I'll be presenting to you the unit probability and statistics for BMA4201. We introduce multivariate normal distributions. First, you recall the univariate normal distribution. Distribution was defined as f of x for a single random variable x is equals to 1 over root 2 pi sigma exponential negative a half x minus mu all over sigma squared. Now, you later considered the bivariate normal distribution. Considering two random variables, x and y, and you had f of xy is equals to 1 over 2 pi sigma x sigma y, then the square root of 1 minus rho, that is the correlation between x and y, then exponential negative a half x matrix minus mu matrix transpose variance covariance, rho of x minus mu y all over sigma y. This is mu x all over sigma x. Then, for multivariate, normal, we have more than two random variables in question. That is the k-variate. The k-variate normal distribution will be given by f of x1 all the way to xk, which is equals to f of matrix x, defined by 1 over 2 pi raised to power k over 2, then the variance covariance matrix raised to power half, then the exponent of negative a half x matrix minus mu matrix transpose, then the inverse of the variance covariance matrix, then x matrix minus mu matrix. This is the definition for multivariate normal, where each of those x is defined as x1, x2, all the way to xk. Then mu is a vector of means of each of the random variables all the way to mu k. And then the variance covariance matrix is defined as sigma 1, 1, which is the variance of the first, then the covariance between the first and the second, and that would continue up to the variance between the first and the last variable. And then this continues, sigma 1, 1, sigma 2, 2, all the way to sigma 2k. This continues down to sigma 1k, sigma 2k, then goes all the way to sigma kk. Let's look at the marginal joint probability function. definition, marginal joint probability function the definition for marginal joint probability function, let x1, x2, all the way to xq, this continues q plus 1, all the way to xk, denote k random variables with joint density function p x1, x2, all the way to xq, then xq plus 1, all the way to xk. So we are partitioning the list of random variables from x1 to xq, then starting from q plus 1 all the way to k, so that we have the first partition and the second partition. Then the marginal joint probability function of the first partition x1, x2, all the way to xq is p1, 2, all the way to q of x1, x2, all the way to xq is equals to summation from xq plus 1 all the way to summation up to xk, probability of the whole set up to xk. So we are saying if we want the marginal distribution of the first set, then we sum the probability distribution of the whole set for the remaining set that we are not interested in. This is when x is discrete, for discrete case. When x is continuous, when x1, x2, all the way to xq, xq plus 1, all the way to xk is continuous, then the marginal joint density function of x1, x2, all the way to xq is f1, 2, all the way to q of x1 all the way to xq is equals to integral negative infinity to infinity, integral negative infinity to infinity of the whole distribution, that is from x1 all the way to xk, then the derivative of the rests of the partition xk. Conditional density, conditional joint probability function definition. let x1, x2, all the way to x cube plus 1, all the way to xk denote k discrete random variables with joint probability function p x1, x2, all the way to x cube plus 1, all the way to xk. Then the conditional joint probability function of x1, x2, all the way to xq given xq plus 1 is equals to xq plus 1 all the way to xk is equals to xk is p1 all the way to q given q plus 1 all the way to k, x1 all the way to xq given xq plus 1 all the way to xk is the same as the distribution of x1 all the way to xk divided by the distribution all the way to k of the remaining part all the way to xk. So if you want the conditional joint probability function, then you will get the distribution of the whole divided by the distribution of the partition other than the one we are looking for. Let x1, x2, all the way to xq plus 1, all the way to xk denote k continuous random variables with joint probability density function f x1, x2, all the way to xq plus 1, all the way to xk. Then the random variables x1, x2, all the way to xq and xq plus 1 all the way to xk are independent if f x1 all the way to xk is equals to f1 all the way to q of x1 all the way to xq multiplied by f of q plus 1 all the way to k x q plus 1 all the way to k. So if to get the overall distribution of the random variables, you can multiply the marginal distribution of each. Then we say that the two are independent. Note, for multivariate, integral, negative infinity to infinity, negative infinity to infinity, of f of x1, x2, all the way to xk, dx1, all the way to dxk should be equals to 1. Just the way we had integral of all x of f of x is equals to 1, even in this case it holds. Example, let x, y, z. So if you have three random variables, x, y, z, then this is a multivariate case because it exceeds 2. Denote jointly distributed random variables with joint density function f of x, y, z is equals to k x squared plus yz x, y, z in the interval 0, 1, 0 otherwise. Now we would like to determine the value of k we also want to determine the marginal distribution of x, y, and z, and we also want to determine the conditional, the marginal distribution of xy, xz, and yz. Solution. We've seen that if you integrate over all x of f of x1, x2, all the way to xk, dx1 all the way to dxk, should get 1 for it to be qualified as a PDF. So here we have 3, we have x, y, z. So we'll argue out that integral, because all of them are in the interval 0, 1, integral from 0 to 1, integral from 0 to 1, assuming the first one is x, y, z in that order going outside, then f of x, y, z dx, dy, dz should be equals to 1. So making replacements for the distribution given, we are going to have integral of k x squared plus yz dx, dy, dz should be equals to 1. So we'll start by integrating x. So this means that we can factor out k. So if I integrate x, I'll remain with the two integrals for y and z. Then integral of this with respect to x, I have to add 1 here, get 3, divide with it. So I have a third x cubed plus, this doesn't have x, so if I integrate it, I introduce x to it. Then I make replacements. Then I have dy dz, should give me 1. So now, making replacements, I have k is integral 1, 1. Then if I put 1, each of these x's disappears to 1. For this, it goes to 0. So when we make replacements for 0, we won't have it. When we put 1, we remain with a third, because this becomes 1, plus yz. You want to differentiate with respect to y, then with respect to z, so that this gives us 1. Now I need to differentiate now with respect to y, so I'm going to have k, then integral from 0. This is the integral with respect to z. Then with respect to y, this doesn't have y, so if I integrate it, I'll introduce y to it, plus it has 1y, so integrating, we have a 1 here, so I add 1, I have a half y squared z. Then we make replacements for y is equals to 0 and y is equals to 1. Then we are remaining with integrating with respect to z. So making that replacement, we're going to have k integral 0 to 1. Then I'll have a third plus a half z. Then lastly, we integrate with respect to z. So it be k. This doesn't have z, so I'm going to have a third z. This has 1z, so 1 here, add 1, divide, I get 1 over 4z squared. Then I make replacements for z is equals to 0 and z is equals to 1. Making that replacement gives us k. Then this becomes a third, and this becomes a quarter is equals to 1. So therefore I have k, the LCM of 3 and 4 is 12, so I have 4 plus 3 is equals to 1. And therefore 7 over 12k is equals to 1, implying that k is 12 over 7. So we've been able to obtain the value of k. So we can be able to now get the marginal distribution. The marginal distribution of x, we are looking for f at x, which will imply, because we want for x only, we need to integrate for the other two. So integral negative infinity to infinity each case. Then f x y z dy dz, so that we remain with the x only. This implies that we get 12 over 7 integral 0 to 1. Our limits were 0 to 1 in each case. X squared plus yz dy dz. So that this becomes 12 over 7 integral 0 to 1. Then we have x, when I integrate with respect to y, this doesn't have y, so it becomes x squared y. Then this has y, so it becomes a half y squared z. Make replacements for y is equals to 0 and y is equals to 1. Then we are remaining with derivative integral with respect to z. So this becomes 12 over 7 integral 0 to 1 of x squared, making replacements, x squared plus a half z dz. Then if we integrate now with respect to z, we have this being equals to 12 over 7 x squared z plus a quarter z squared. Now make replacements for z is equals to 0 and z is equals to 1. We have 12 over 7 x squared plus a quarter. And this works for x in the interval 0, 1. You notice that now we've remained with an expression for x only. Let's now get the marginal distribution. Of xy. Now, since we want the marginal distribution of x and y together, then we are looking for f1, 2, 1 for x, 2 for y, of xy is equals to, we will now integrate with respect to the remaining one, that is z. So we have f xy z dz, which implies 12 over 7 integral 0 to 1 x squared plus yz with respect to z. This becomes 12 over 7 x squared plus a half y for x and y in the interval 0, 1. Now with this, it is possible to obtain the conditional distribution of z given x is equals to x and y is equals to y. That should be given by, we said you get the total, the overall distribution of the three, you divide by the marginal distribution of these two, of x and y. So this will be 12 x squared plus yz, 12 over 7 rather, 12 over 7 x squared plus a half y. These and these go, so that we have x squared plus yz all over x squared plus a half y. And this works for z in the interval 0, 1, 0 elsewhere. That is the end of lesson 1.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.